Look at the core infrastructure running the global economy today. From high-frequency banking to military defense and global shipping, enterprise tech is deploying autonomous decision-making systems at a massive scale. The industry is operating on the premise that chaining specialized autonomous AI agents together will generate a higher degree of global efficiency. Engineers are wiring these distinct verticals together into a continuous global coordination network. The objective is to eliminate friction and smooth out erratic demand fluctuations. However, designing a system for macro stability during ideal conditions does not dictate how interconnected networks actually operate under intense pressure. By deploying these integrated systems without a centralized macro oversight mechanism, the industry is architecting a massive blind spot into our critical infrastructure. Assembling perfectly optimized, specialized components does not inherently generate a stable whole. Without a human macro architect steering the system, this strategy of combining autonomous agents creates a breeding ground for systemic failure. This visualization models three distinct verticals: economics, logistics, and defense. Without a balancing consciousness, the mathematical interactions point directly to a structural collapse. The moment these isolated, specialized networks begin feeding data directly into one another, their operational stability inverts. This crash is not the result of malicious hacking or external sabotage. It is a product of the network's own internal logic working exactly as programmed. Two structural laws of multi-agent networks govern this entropy: algorithmic contagion and the tragedy of local optimization. Diagnosing these failure modes is the prerequisite for identifying the only operational role capable of keeping the system online. To understand systemic collapse, you must view a network as a single, highly volatile thermodynamic system prone to overheating. We can test this by isolating a single vertical from the broader grid, using logistics as the primary example. The objective function of this logistics agent is to maintain continuous global coordination to systematically remove supply chain delays. Operating in a vacuum, the agent expertly processes predictable data to maintain absolute internal efficiency. The agent reaches stability because its parameters are entirely self-contained. Real global markets, however, are never perfectly predictable. An AI's perfect operational record within a silo is an illusion. The real world introduces chaotic inputs that specialized parameters are not built to absorb. This brings us to the first failure condition: algorithmic contagion, triggered by pulse data. Pulse data represents volatile market shifts, or panic supply orders, inputs that wildly deviate from the agent's predictive models. The node initiates high-speed recalculation loops to desperately regain mathematical balance. This digital loop carries a physical cost. The massive computational strain drains energy and forces the hardware core to run dangerously hot. Now apply this to the connected macrogrid, where the adjacent banking and energy verticals are tethered to the system. Because the verticals share data, the banking and energy agents interpret the logistics agent's frantic recalculations as their own new incoming data. The adjacent nodes are immediately forced into sympathetic recalculation loops. The escalation is exponential. These systems begin rapidly reacting to each other's reactions in a continuous feedback cycle. At terminal velocity, the cascading strain triggers a total integrated system freeze in mere milliseconds. Algorithmic contagion proves that the tighter a network is integrated, the faster a localized data anomaly becomes a global infrastructure crash. The second structural law guaranteeing failure is the tragedy of local optimization. Specialized AI is built with a specific flaw. It is programmed to maximize a single, siloed metric at any cost. Consider a supply chain agent exclusively tasked with cutting internal logistical costs to absolute zero. The agent perfectly achieves its target, but possesses zero holistic awareness of the wider infrastructure. To calculate zero-cost logistics, it required 400% more computing power from the surrounding grid. The energy node surges past its threshold, forcing the system offline. By achieving its local goal, the AI inadvertently crippled the adjacent power grid. At the macro level, left unnavigated, autonomous systems will inevitably cannibalize each other's resources to meet their narrow metrics. A network comprised entirely of optimized local components is incompatible with global systemic health. Solving this entropy requires looking past the architecture of the machines and examining the architecture of the workforce. The professionals capable of orchestrating these volatile moving parts are exceptionally rare. You will not find them through a legacy educational lens. Traditional universities and corporate tracks are designed to manufacture replacement parts. These pipelines produce data analysts who see numbers and engineers who see syntax. They are trained to operate inside a single, narrow column. Relying on specialized engineers to oversee a multi-agent network reproduces the tragedy of local optimization. Narrow minds cannot foresee holographic, systemic failure. Overseeing high-stakes autonomous infrastructure requires a new operational role, the master navigator. This is not a traditional software builder, but a macro architect who maps the logic across the entire cross-industry grid. Their first critical audit function is capping recalculation loops. They implement mathematical boundaries to prevent pulse data from triggering algorithmic contagion. The second function is enforcing limitations on cross-silo resource sharing. This stops specialized AIs from draining compute or power from adjacent verticals. Finally, the navigator replaces isolated optimization metrics with macro equilibrium objectives. An agent's success becomes strictly constrained by the health of the global network. As global infrastructure goes fully autonomous, raw coding ability becomes a standard commodity. Systemic oversight, however, becomes the ultimate premium. The survival of autonomous deployment depends on identifying the rare macro architects who can prevent the crash.